Hello students, in this video we will discuss how to solve one-dimensional wave equation. So first we look the general form of one-dimensional wave equation. It's del 2u upon del x square is equals to 1 upon c square del 2u upon del t square. Here x and t are independent variable where u is dependent variable, depends over x and t. And here c is a non-negative real constant. Or we can rewrite this equation as del 2u upon del t square is equals to c square del 2u upon del x square. Now look some problem based on this equation. So first problem says show that a one-dimensional wave equation del 2z upon del x square is equals to 1 upon c square del 2z upon del t square has solution of the form a into exponential plus minus iota nx plus minus iota nc t. Here a is arbitrary constant and n is also constant. So we have to show that the general solution of a wave equation, one-dimensional wave equation, contains term like exponential plus minus iota nx or plus minus iota nc t type. So as we have the general wave equation del 2z upon del x square is equals to 1 upon c square del 2z upon del t square, say equation number 1. Now using the separation of variable method, we assume that the solution of this equation is z is equals to x into t, where capital X is some function of x and capital T is function of small t. Now we will differentiate this z partially with respect to x and t twice. Hence, we can get the value of del 2z upon del x square and del 2z upon del t square. So, when we differentiate z partially with respect to x, we get del z upon del x is equals to dx upon d of x. That's ordinary derivative, not a partial derivative, because x is x depends on a single independent variable, small x. So, here we use ordinary derivative dx upon d of small x into t using u into v rule. Again, further we differentiate this equation partially with respect to x, we get del 2z upon del x square is equals to d2x upon dx square t, or we can rewrite it as del 2z upon del x square x double prime t. Similarly, we will differentiate this equation with respect to t partially, hence we get del z upon del t is equals to x into del t upon t, implies del 2z upon del t square is equals to del 2z upon del d2z upon dt square into x, or we can write it as del 2z upon del x square is equals to x into t double prime. Now we will put these value of these derivative in equation number 1. We get del 2z upon del x square is equals to x double prime t. So in left hand part, x double prime t is equals to 1 upon c square into x t double prime. Or we can rewrite it as divide this equation with capital X and capital T, we get 1 upon x d2x upon dx square is equals to 1 upon c square t d2t upon dt square. So they both are independent separate term in x and t, so we can assume these equals to some lambda constant. Now we use first and third fraction, we get 1 upon x d2x upon dx square is equals to lambda, hence we get d2x upon dx square minus lambda x is equals to 0. And now using second and third fraction, we get 1 upon c square t d2t upon dt square is equals to lambda. It gives us d2t upon dt square minus lambda t c square equals to 0. Now we will solve these equations one by one. As they both are second order linear differential equation, ordinary differential equation with constant coefficient, and as right hand part is 0, so only CF is their solution. So its auxiliary equation will be m square minus lambda, its auxiliary equation is m square minus lambda c square, which leads us some solution. But here, as lambda is constant, it can take any value. It might be positive, it might be negative, or it might be 0. So one by one we consider every case. So when lambda is equals to 0, in case of lambda is equals to 0, equation second become d2x upon dx square is equals to 0, and similarly d2t upon dt square is equals to also 0. Solving the first d2x upon dx square is equals to 0, we get x is equals to ax plus b. We are to integrate it twice. First, when we integrate it, it gives us dx upon dx is equals to some constant, say a. Further, when we integrate it, it gives us x is equals to ax plus b, some another arbitrary constant. Similarly, when we integrate d2t upon dt square twice, we get t is equals to ct plus e. So here it's not x, it's t. Okay. So ct plus t. Now we will put in solution u is equals to ax plus b. Actually this is z. As we assume solution z is equals to x into t. Here z is equals to x into t. So that's why there is z in place of v. This is z is equals to ax plus b plus into ct plus d. This is multiplication sign. So it contains algebraic terms, but as we are discussing wave equation should contain sine or cosine term. So there is no sine and cosine terms, that's why we will discard this solution. Now if we assume lambda is equals to n square, in that case we get d2x upon dx square minus n square x is equals to 0. And when we solve it, we get x is equals to a exponential nx plus b exponential minus nx. Its auxiliary equation is m square minus n square, which gives us two roots, m is equals to plus minus n. That's why CF will be a exponential nx plus b exponential minus nx. Similarly, from second equation, we get d is equals to c exponential nct plus d exponential minus nct. And the solution z is given by a exponential nx plus b exponential minus nx into c exponential nct plus d exponential minus nct. Again, it does not contain sine and cosine terms, so again we will discard or reject this solution. Now in third case, we assume lambda is equals to minus n square. In that case, the previous second equation becomes d2x upon dx square plus n square x is equals to 0. And the second equation becomes d2t upon dt square plus n square c square t equals to 0. Now again we will solve it using ordinary differential equation with constant coefficient. We get ax is equals to a1 exponential iota nx plus a2 exponential minus iota nx. As its auxiliary equation is m square plus n square, whose roots are m is equals to plus minus iota n. So it becomes x is equals to a exponential iota nx plus a2 exponential minus iota nx. Similarly, from this equation we get t is equals to b1 exponential iota nct plus b2 exponential minus iota nct. Now we will put these two solutions in above assumed solution, which is z is equals to x into t. When we put it here, we get z is equals to a1 exponential iota nx plus a2 exponential minus iota nx into b1 exponential iota nct plus b2 exponential minus iota nct. Now when we solve it, here we get four distinct terms. These are first a1 b1 exponential iota nx plus iota nct. In second term, we have some another multiplication of arbitrary constant a1 b2 and exponential of iota nx minus iota nct. Whereas in third term, we have index of exponential is exponential minus iota nx plus iota nct. And in fourth term, we have exponential minus iota nx minus iota nct. So taking a1 b1 as c1, a1 b2 as c2, a2 b1 is c3 and a2 b2 is c4, we get this term. Here we can rewrite this term as z is equals to c exponential plus minus iota nx plus minus iota nct. When we choose both positive we get first term, when we get both negative we get second term, fourth term, sorry. When we get positive and negative we have second term, and we have negative and positive we have third term. Hence the problem is we have proved is the solution of one dimensional wave equation contains the term exponential plus